Hello everyone, I'm Jason Sikes, aka the Tech Rancher, and this is my homework solution for lesson number 41 from the course called Raspberry Pi Pico W by Paul McWhorter. Paul does a really good job at doing multiple different courses. You can find him on YouTube at looking up at Paul McWhorter, or you can check out his website at www.toptechboy.com. Alright, enough about Paul. Let's get into what we're going to be working on today. Let me show you right here. Before we get too far in, let's look at the wiring diagram. Let's see how we do this wiring diagram. Alright, for the, we're right here for this MPU 6050. You can see the VCC hooks up to the power rail right over here. And then you can see that the ground hooks up to the ground rail. Then we have right here, we have the SCL, and it hooks up to the GPIO pin 13, that white wire right over here. And then we have the SDA, that's the green wire right here, hooks up to the GPIO pin 12. Alright, now let's look over here at the SSD. This is a 1306, and we see that we have the power rail, the VCC is hooked up to the power rail. The GND is hooked up to the ground rail. And then we come over here to the SCL, the blue wire coming over here. That's to the GPIO pin 3. And then the SDA, that's the yellow one right here. The SEA pin is hooked up to the GPIO pin 2. And then we have for the Pico W, we can see that we have the ground coming to the ground rail. That's actually physical pin number 3. And then the power rail, which I'm kind of in the way here, but coming on right on the edge of my screen here, and that's the physical pin. I believe it's 36. Yeah, 36, and that comes all the way over here to the power rail. All right, now since we have the MPU 6050 hooked up along with the SSD 1306, let's look at kind of what all we're supposed to do now. Paul had asked us to take what he had taught us on lesson number 41 and to figure out the tilt. And what he wanted us to do is figure out the tilt for, on the X and Y axis. And we're going to be using Z to help do the calculations on it. But the Z axis is the azimuth, which this MPU 6050 does not have a magnetic compass built into it, so we won't be able to do the yaw. But we're going to do the X and Y. So we're going to say that the X will be the pitch and the Y is going to be the row. And here's how we're going to define that. If we can look at our diagram back here, this is our small edge and we have one on the opposite side. This, and the way how the Pico W is laid out, this is going to be our pitch. So pretend this is a fuselage of an aircraft. And this could be your cockpit, and back here will be your tail section. This is your imagination. Okay, anyway, so if we lift this end up, then we're going to be pitching upwards. And if we lower it down and raise the opposite end up over here, then we're going to actually be decreasing. And then our long edge of our breadboard and the opposite side. So if we imagine this ditch that we have in between our breadboard right here, if that was stabilized of our axis, of our y-axis, and we were to row like a teeter-totter from this top part over here to the and raising that up. So like if we grab the hold of the back of the breadboard and raise that up, that would be called a row. Like on a fuselage, if you have wings coming off where these wires are located on the sides, you'd actually be rowing on the length of the fuselage. And so it'll be kind of like banking, have your ailerons being able to move, causing one wing to get more lift, another wing to get more drag, and therefore it would bank or roll to that direction. So that is what Paul wants us to do, is to find the angles of our pitch and our roll. Well, that sounds kind of complicated because this MPU 6050 reads acceleration and a gyroscopic system on it. It does not tell you what angle it's going. That's where trigonometry and math comes in play. About 2 lessons ago, well, if you go back 5 lessons ago, Paul had started in teaching us some trigonometry. And this trigonometry is very crucial for being able to figure out how to take this accelerometer, or the acceleration of the vectors, and figure out what the angle would be. Without going really wordy, I'm going to read my notes to keep on topic. There we go. All right, so you're going to see my eyes probably darting over here to the side, and I'm trying to read my notes, but here we go. Hang with me. All right, let's start out with this. Let's start out with some variable names and understanding what we got here. Okay, we have an acceleration. Acceleration is the rate of change in velocity. It is a vector, meaning it has both the magnitude and direction. The magnitude of acceleration is measured in meters per second squared, which is m/s to the square or power of 2. The direction of the acceleration is indicated by the angle between the acceleration of vectors and a reference axis, which is typically a horizontal axis. Some people are probably scratching their heads and saying, man, you lost me. Hey, I got a picture to go with this. Let me pull that picture up here. This will kind of help us out. Hey, there we go. All right, let's look at here. Computing the rotation angle. This has tons of lines. What's going on? Oh man, all right, let me see if I can do. Let's see if I can confuse you more. I have some people that make some good comments, and I really appreciate it, and it's taught me a lot to be able to try to teach people better, so I'm going to give it the best shot. All right, if we use our right-hand rule as Paul taught us, wow, I don't think if I'm going to do this very good, but if you lay it out here, using our thumb up, so it's pretending like you're pointing with your pointer finger actually pointing to the side. Whoops, let me get over here where you can see this a little bit. I don't know how to do it, so I'm going to try. Here, hang with me. Okay, we're going to use this one right here as our x-axis. See if you can, I'm going to try to look at my, try to look at my picture. This is the x-axis. This is my pointer finger pointing straight out. And then my middle finger is pointing to my left as I'm pointing straight out. This is what we're going to use as our y-axis. And our thumb coming straight up is what we're going to use as our z-axis. And so you can kind of rotate it around, but as you're looking at it and you put it towards you, your pointer is going to your left now, and now your middle finger is coming towards you, and your thumb is coming straight up. Okay, this is like what our picture shows right here. So we have the x going to the left, our y coming towards us, and our z coming up. So this is my pointer finger, this is my middle finger, and this is my thumb. That's what Paul was trying to teach us about using the right-hand rule. Right-hand rule shows us our vertical three-dimensional axes. All right, with that said, you can see that there's a dotted box around here, and then it looks like it's cubed. And the cubed is actually trying to show the movement or the acceleration that the box had performed. So our R is representing the rotation or movement of this box. Or actually, we're going to say square, but it looks like a box because I've indicated the movement with it. So you can see there's a line right above the vector of R, and it says R, X, Z. And what this means is it's the rotation of our X vectors and our Z vectors coming together to point. This is where the end point of the vectors have produced with the movement. And so now we want to know the AXZ. This is what Paul was asking us to calculate during our acceleration. So this movement was through acceleration, and this arc right here is the angle that we want to calculate. So there's a couple of different ways, and the way that Paul had spent the time and the resources to teach us through trigonometry is the way how I'm going to address this. But there's, as you can say, there's multiple ways to skin a cat. Sorry, Charlotte. Okay, so with that said, we're going to look at the tangent, and then we're going to look at the tangent too, which is, we're going to say the arctangent, because we're needing to know the angle of it, or the theta of it. So how? Well, here's how we're going to do it. Here's another um, another definition that we need to look at. Acceleration angle is an angle between the acceleration vectors and the horizontal axis. So acceleration vector and a horizontal axis right here. And then it can be calculated using the following equation. So we're saying the theta equals the tangent, or the actually arctangent with a y, or we could say y, the y-axis, which, okay, what is our y-axis here as we're representing here? What would be our y-axis? Well, we have the y-axis sitting right here, and we have x-axis, and we have z-axis. So how are we calculating this, the y-x-z on this, on the three-dimensional vectoring? Well, okay, we moved in our three-dimensional plane forward here, and we're going to x, we're going to x up and y over, z over, and then our y would be if we had did a row, but we're doing an actual, when we're figuring out our x, we're doing a pitch incline. So we're going to say our y and our x, but we're going to be calling it x and z. So kind of like you can see up here, we're using x and z of this, because y is not in play with this, but the z is, and the x is also too. So I know Paul had told us y over x, but he also did tell us that our triangle could be rotated at any different position. And so he was trying to prep us to help us understand that it may not always be in that formula that we think it is for the tangents. So this is why we're going to do x over z. So now with the x over z, you can put that into your calculation form, and you can take your x, or acceleration of x, and put it right here on your x, and an acceleration of z, and put that right here for the rz. That would give you your be coming out as a radiant. So then now we're going to have to do our calculation from radians to degrees. And if you can remember that if you come out with radians, you always times it by 180 divided by pi, and that would give you your degrees. I'm going to refer back here to my notes to make sure I'm going with it. Let's do a mathematics with it here. It's going to be really simple, but it's going to be mathematics to kind of go with this here. So we're wanting to know the theta of this. So we're going to say our x is going to be 10 meters per second squared, and our z is going to be 2 meters squared, which, let me hold up here a little bit. Let me tell you that the MPU 6050, if we use our library, it comes out as g-forces and not this. This can still be used in our g-forces. Meter squared is if you did it raw. If you're going to convert it over to g-forces, you use 9.81. So you take your calculations and you times it by 9.81 to get your g's, because that's what the gravitational pull calculation is. In this calculation form, we're using meters per second squared, because that is a raw data. If you go ahead and use it in G form, I noticed that I didn't have, which I'm sure is a minute amount of difference, but I calculated it as in G and did not convert it over, and it's indicating, as you'll see a little bit later here, that it's indicating correctly. Okay, get back here to what we're doing. Okay, now we want to calculate that angle, and so what we do is we take 10, which is our x-axis, 10, and we divide it by 5, which was the z-axis. which you take 10 divided by 5 is 2. And so then that would give us the remaining of 2. And now we're going to take that 2. Hold on, my brain kind of went crazy here. Yes, that's 2. And then we're going to divide it by times 180 divided by pi. And that gives us 63.4 degrees. I'm sorry, I had a little, my brain kind of went bye-bye there, but luckily I looked back at my notes. That helped me out. Okay, so then that was our first example of how that worked. And so with that said, I said there was a more than one way to do this calculation, and that what we just did was with tangent 2, or the arctangent 2. And the reason why arctangent 2 is because it uses arctangent uses vectors. So you could say the vector we'll just look right here at the picture before I get us more confused. So the arctangent 2 is saying where we're going to use a vector of rx and rz. So it would be like saying x and y, but we're saying x and z because we're using z as our y because we're not wanting y right now. So the x and z, and we put it into our math form. So, and you'll see it here in a little bit in my code, but let's say right how we would say math dot a tangent 2, and then we put it in our colons. We would say rx comma rz, close that, times 180 divided by pi, our math dot pi, and that would give you your degrees, unless you're wanting radiant. And then you wouldn't do that. You wouldn't do the last step of timesing, dividing. All right, back here to the notes, and we solved that first little one. And okay, so then another way would be to use arctangent, and then you'd have to be able to. That's when you'd have to use square, and without trying to confuse you too much, because this is the easiest way. But the other way is for you to get your answer, you're going to have to take your numerator, and so your denominator would stay as a whole number, and then your numerator would be having to be squared to the power of 2 for it, and that's confusing if you're not really wanting to get into very much math. All right, with that said, let's get over here to my code. All right, this is actually the one with the squaring. And that's going to probably confuse a lot of people because I didn't really get into too much of that. But I'll just scroll down here and show you my function when I'm talking about here. So I had labeled it as a magnitude, and then I'm saying I'm squaring the x-axis to the power 2, the y-axis to the power 2, adding the z-axis to the power 2. Then I'm putting that into my formula of the arc sine, math.arcsine, and I'm using the y for the pitch, and divided by the magnitude times 180 and math.pi, and then rho would be the arc sine of the x-axis divided by my square root of magnitude times 180 divided by pi. All right, let me pull up the camera here. And down here, you can see this is where I'm going to have a printout. I'm going to say over printout because trying to tilt the board, you're not going to be able to read the SSD very well. So keep your eye down here and you'll be able to see the printout too. I'm going to go ahead and start this. And you can see that we're already printing out. And you can see it's not really going to 0. And one of the problems I'm having with that is because my wires are pushing up on my MPU 6050. And so it doesn't always come out correctly. You can see that we're reading right here, but then if I tilt, or actually this will be our row, because I said the long lines of our breadboard is going to be our row of our plane, and you can see that we are calculating it, and there's 35, 30, 39, 40, 42. 50, 60, and it's keeping on going. And see, that's I'm keeping on going, and I got 70, 80, and we're coming up, and we're almost somewhere in there 90. Oh, they're almost. That's one thing I noticed with this doing this calculation with the square root is it's really touchy when you get around the 90 mark. But now I'm slowly coming back, and you can see that it's starting to equalize. And I rotate the other way, and you can see that it's actually changing down here. Now we're negative because we're rotating on the opposite side. We're coming closer to 80. There's 80, and then we're coming closer to 90. And I'm hitting my wires, and it's causing on my breadboard, and it's harder for me to move it. But there's 91 or 89. Sorry, I thought I saw 90, but anyway, okay. Now back here, and let's do our pitch. Let's try to reset our camera here, and then I'm gonna raise it up. Oh, we're climbing. Oh, actually, it says we're diving, but anyway, ignore the negative. I had apparently got that rotated wrong. And you can see that we're increasing. There's 50, and there's 60, 70, and coming up on 80, and we're going to get closer to 90. Oh, that's all 89. Okay, now it's coming back down, and let's raise up the other way, and you can see it's also moving, coming up closer, 60, 70, there's 80, and my finger rotated off that board, and there, that's all 80. That's where it's bouncing around a lot. Okay, enough of this one. I'm going to show you the other one with the arctangent 2. This one I prefer better. It's actually a lot more accurate is what I figured out. But you can do it the other way too. But this is the other one. So now let's go back over here, reposition this where we can see. And I'm going to start this one up. You can see that it says the A tangent 2 on my SSD. And now let's do the row. And you can see here on this that we are rowing. And there's 50. Now we're coming over here to 70, 80. And there's our 90. And look, we can go past 90. We can keep on going with this formula. That's one that I like about this too, is because when you're doing the vectors, you keep on reading the vectors instead of trying to do the actual arctangent. And then, okay, now let's bring this back, and then let's turn it the other way real quick. I'm using a lot of time here. There's 90, so I'm going to go ahead and bring it back. And then now we're going to do the pitch. And you can see I'm already at 30, 40, 50, 60, 70, 80, and there's 90. Okay, and do it the opposite direction really fast. That's a major climb. Major climbing. Whoa, there we go. All right, there's 90. And we can keep on going, as I said, because you're reading the vectors here. And that's what I really like about it. And then you can see, hey, it all went wonky over here on my X, on the roll. And that's because how Paul had told us about how the MPU works. And when it's reading the capacitance of it, and when it's all messed up because of the wires, but when you read the capacitance of it, when it flips, and now it's not reading the X, it's reading the Z, and so that's why it's or the Y. I mean, it's Y is flipped over, and Paul showed Paul showed us that on his graph, where it had when he was tilting it, it got beyond a point that the X and or the Y and X rotated and the Y and Z rotated. That's the same as what this did here. Alright, this was a really long one, guys. And thanks for hanging around and sticking with me and learning more about this. But to just kind of summarize this as best as I could, is the arctangent 2, which is part of our tangent, but this is the arctangent 2, uses the vectors. I had described at the very beginning of it, uses the vectors. Why the regular arctangent will use, for your numerator, you have to do the square root with a power of 2. So square root of it, which I named mine as a magnitude. That's the difference between the two. The easiest one, which is still math, but it's just the easiest one for the formula, is an arctangent 2. If you have any questions, feel free to leave comments down below. I'll do my best to try to respond back to them. Until next time, be safe out there, everyone.